Imagine looking at a massive steel node on a suspension bridge. You have heavy steel cables pulling simultaneously in different directions, creating a web of competing forces. To ensure that joint won't tear apart under stress, an engineer has to take all those chaotic, multi-directional pulls and calculate exactly where the total weight is headed. They need to combine them into a single, equivalent vector, called the resultant force. The most reliable way to do this is to break every diagonal pull down into an isolated horizontal component and a vertical component. Using a basic right triangle, you multiply the force by the cosine of the angle to find the x value, and by the sine of the angle to find the y value. But there is a trap here. Standard sine and cosine equations only work seamlessly if you measure your angles starting directly from the positive x-axis. Translating physical geometry into rigid, correct coordinate math is the precise skill required to decode complex structural forces and prevent failures. To resolve any complex system, we follow a strict 5-step engineering checklist. Set your axes, find your true angles, resolve for x and y, sum the components, and calculate the final resultant. This vector diagram shows a 3-force problem, with distinct pulls of 350, 800, and 600 newtons acting on an origin point. Looking at the 800 newton force, we need to establish its true angle. We don't just use the 45 degrees shown on the chart. We find its exact distance from the positive x-axis by adding the 25 degrees below it, giving us a true working angle of 70 degrees. The 600 newton force introduces a new wrinkle. You can either measure a true angle of 150 degrees from the positive x-axis, or use the local 60-degree triangle provided. If you use the local triangle, you must manually apply a negative sign to your x equation to accurately represent the force's physical pull to the left. Once you calculate each vector and tally the columns, you get your final summed components. The net pull in the x direction is 290.8 newtons, and the net pull in the y direction is 1419.3 newtons. Before we move to the final step, pause the video. Use the Pythagorean theorem and the inverse tangent function with these sums to calculate the total magnitude and angle of the resultant. Your math should give you a final magnitude of 1449 newtons, pulling at an angle of 78.4 degrees. By methodically breaking down each diagonal force into isolated, independent x and y columns, multiple competing vectors collapse into one predictable reality. This complex vector diagram shows a 4-force system designed to test exactly where these calculations usually break down, featuring vectors anchored deep in the negative quadrants. Notice the 30 newton force. Because the 50-degree angle is measured from the y-axis rather than the x-axis, the standard trig equations flip. You must use sine to find your horizontal x component, rather than cosine. Even more importantly, look at its physical direction. Because this specific vector pulls down and to the left, negative signs must be manually assigned to both its x and y calculations. When we resolve all 4 vectors and sum the columns, our final coordinate system shows an x value of negative 11.59 and a y value of negative 24.75. Because both final components are negative, the physical resultant vector has to point down and to the left. Regardless of the raw angle output your calculator spits out, that negative signature tells you the true answer exists strictly in the third quadrant. When resolving any system, always verify your reference axis before reaching for a trig function. Manually assign your physical negative signs and map your final quadrant based entirely on the component signs. Mastering the principle of resolution allows an engineer to look at a chaotic cluster of forces and distill it into a singular, absolute mathematical truth.